Here are the answers to the gas assessment. Now, you wouldn't have had all of these questions. I think you had about 9 of them. These two are very similar. They're looking at partial pressure of a gas in a mixture. The partial pressure just refers to the part of the total pressure coming from one individual gas when I have a mixture of gases. And that fraction of pressure will be dependent on the fraction of particles from that particular gas, or we can refer to that as a mole fraction. It's kind of like a percentage, but we don't need to multiply by 100. So it's the moles of a particular gas divided by the total moles of gas in the mixture, and then we use that fraction to figure out the partial pressure of the gas. So if 50% of the particles in a mixture are nitrogen, 50% of the collisions are nitrogen, and 50% of the pressure is nitrogen. If 25% of the particles are hydrogen, then 25% of the collisions are hydrogen and 25% of the pressure is hydrogen. Now, it didn't matter the identity of the gas. It's just about the number of particles and the number of collisions. Then there were a series of questions that referred to a table with 4 gases, A, B, C, D. They are at the same temperature, and they are in identical rigid containers labeled A through D. The best explanation for the lower pressure in container 4 is that there was one of these kind of similar on a practice quiz that, we expect particles to collide, and if they're at the same temperature, they have the same amount of average kinetic energy, and so the same amount of collisions should cause about the same amount of pressure. Now, most of these gases are producing about 1 atmosphere of pressure. We'll deal with gas B later, but notice then that D is just a little bit less than what I might expect. That's due to those intermolecular forces. A lower average speed, a lower average speed would mean that it's maybe like a heavier particle. It's not the heaviest particle. Occupy a larger portion of the container volume than the other 3 gases. No, because actually the carbon disulfide might be about the biggest molecule. And really the volume of the particles themselves is pretty insignificant compared to the volume of the container. SO2 molecules are not nonpolar, they are very polar. So this one you might have had to sketch the dot structure. And that when I find a polar molecule versus the other 3 that are nonpolar, these gas particles aren't really supposed to be attracted to each other. But if they're polar, then the intermolecular forces are a little bit more significant. The particles are a little more attracted to each other, and then the pressure might not be quite as high as I expect. Same for gases. Which of the following is true of the gases listed in the table? These are all referring to average kinetic energy. Average kinetic energy refers to temperature. So as long as these gases are at the same temperature, they have the same average kinetic energy. That's like the force being applied upon these particles. Now, obviously, that same amount of force does not translate into the same speed or velocity. That depends on mass. So now my heaviest particle is going to move the slowest, and my lightest particles are going to move the fastest. The same amount of energy is being used to push the particles, but if it's pushing more mass, then those particles just aren't going to travel as fast. But here, average kinetic energy refers to temperature. Here was maybe the trickiest of these that dealt with this little table. Of the gases in the table, the density of the gas in grams per liter is greatest in which container, basically. Most common wrong answer was probably C, in that if you have the most mass, and it does say that they're in identical rigid containers, and so I don't know the volume, but if they're all identical rigid containers, they have the same volume, and so then density would be dependent on the different masses of the particles. And so the most common wrong answer was C, where you were thinking along the right lines, and I got to find the most massive particle. Here's where we got to look at that pressure of gas B. Did you catch that gas B has twice the pressure? And so if these particles are at the same temperature and they're in containers that have the same volume, well, the same number of particles should cause the same number of collisions, which would cause the same pressure. But the pressure is doubled for gas B, which then must mean that gas B has twice as many particles. Oh man, there must be twice as many particles in a container that has the same volume. So I don't know if they're 1 liter containers or whatever. So if there's twice as many particles, and again, I don't know if it's exactly a mole or half a mole, but let's say it was a full mole. Well, if there's twice as many particles of CO2, that's going to give me 88 grams of gas in, let's say it's a 1 liter container. If it were half a mole of gas, it would be the same issue, that if each gas had half a mole of particles in the same container at the same temperature, then there'd be the same amount of collisions, and that should create the same amount of pressure. But whatever number of particles was present, there was twice as many of gas B, and that's what caused double the pressure. And so I just kind of have to like multiply that mass by 2. So gas B would have had the greatest density, the most mass, and they're all the same volume. What a tricky little question there, huh? Moving on. This question referred to mole ratios in a balanced equation where everything was gas. The reactants were gas, the products were gas. They gave me half a mole of butane and 3.25 moles of oxygen in a closed container fitted with a movable piston, which just means that that piston can move up and down depending on how much gas, the temperature of the gas, the pressure of the gas. The mixture sparked, allowed to react as completely as possible according to the reaction. Which of the following is true after the product gases return to the original temperature and pressure? Okay, so I did just kind of look at these molar quantities, and it does correspond to the ratio in the balanced equation. It's just that everything would have been divided by 4. So half a mole, 3.25 moles. It's just like a quarter of what I would have in the balanced equation. So I do have a stoichiometric ratio, which means I don't need to deal with any excess reactant. There will not be any excess oxygen or butane left over, which means that when this reaction is complete, the 2 reactants are completely consumed, and all I have would be products. So then I just kind of looked at the ratios in the balanced equation, and it's going to be the same general ratio, whether I use the 2 to 13 or whether I carry that out with my 0.5 and my 3.25, that proportionally there's more total moles on the product side, which should mean there's more collisions. And if this is a movable piston, then more collisions are going to cause that volume to expand. And so the piston should move to a higher position, greater number of particles on the product side. And again, it does say that we return to the original temperature and pressure. So that was kind of key to this one too. So that then the volume in that compartment of gas would solely be dependent on the number of particles. Kind of similar was this guy. And again, you may not have had all of these questions, but then there's some other great practice questions for you. I've got carbon monoxide and oxygen producing carbon dioxide. The reaction is allowed to occur in a rigid, closed reaction vessel. Which of the following statements correctly predicts the change in pressure as this reaction goes to completion at constant temperature? Okay, so now I'm going to have a situation where the volume is constant, the temperature is constant, so the pressure will be dependent on just the number of particles. And so I just counted the number of particles before and after. So after I have less particles, less collisions, which means that the pressure should go down. Here's a question that was commonly missed, and I think, if anything, like I bet you were close. I bet you were really close. And when you see the right answer, you're gonna slap yourself in the face and be like, what was I thinking? It's stoichiometry. So you've got 12 liters of nitrogen and 12 liters of hydrogen allowed to react in a flexible, closed container at 25 degrees. When the reaction is complete, what is the total volume of the container? So flexible container, meaning that it can expand. And they do say that the temperature is constant. All right, so then the volume is going to be dependent on the number of particles in the container. And so I can use the mole ratios from the balanced equation. And so as long as our conditions are constant, and if the container can expand, then the pressure inside the container will also remain constant. So I have a constant temperature, a constant pressure, and so I can use those 12-liter volumes as like a ratio of particles. That the volume must be dependent on the number of particles, which then lets me use the ratios from the balanced equation. So just by inspection, I can tell you right away that hydrogen is the limiting reactant, because I need 3 times as much hydrogen. So under similar conditions, if I have equal volumes of gases, they would have the same number of particles. But I need 3 times as much hydrogen, and I don't have that. So hydrogen is my limiting reactant, and then I use the ratios in the balanced equation to figure out how much product is formed. And then we can't forget about the excess this time. I do not have a stoichiometric ratio. So I mean, one of the common wrong answers was 8. Oh, dang. And you were on the right track if you picked 8, because you found the limiting reactant, and then you used that limiting reactant and the ratio in the equation to figure out how much product was formed. And again, we can use the ratio as a ratio of volume, because the volume should be directly proportional to the number of particles if we're at the same temperature and pressure. Okay, so yeah, there would be 8 liters of ammonia produced, but then we also have some excess nitrogen. And so, unfortunately, 12 was another one of the choices here. How rude, almost. And if you picked 12, I bet you were really, really close, and that you recognize that there would be some excess nitrogen. And so you used the limiting reactant, you used the 1-to-3 ratio between hydrogen and nitrogen, and you got 4 liters of nitrogen. And so then maybe you added like 4 and 8 and got 12. Oh, you were so close. We just kind of misinterpreted the 4. That's 4 liters of nitrogen needed, or 4 liters of nitrogen that get reacted, but you have 12. So you really have 8 liters of nitrogen excess. And so the final volume is dependent on the number of particles, which would include the excess nitrogen plus the ammonia produced. 16. Oh man, I bet we were really close on that one. Next question had a little graph, and it showed me 2 gases. And to interpret this graph, the only point that we really care about is that peak. That shows us the speed, the average speed of most particles. The highest percent of the molecules will be like at the peak, and then if I follow it down, it tells me the average speed or velocity. Okay, now the area under each graph should be about the same, and that we're comparing the same sample size, the same amount of particles, but here it looks like they have different speeds. And so gas X has a lower speed. Gas Z is traveling at a higher speed. Speed and velocity depend on mass. So gas Z is a lighter gas. It's got a smaller molar mass. That on average, particles of gas Z are traveling faster. Average kinetic energy is temperature. So as long as they're at the same temperature, they have the same average kinetic energy. And for these graphs, the volume under the, or I should say the area under each graph should be the same, representing the fact that the samples have the same number of particles. Here's another one that's kind of similar. The graph above shows the speeds of helium molecules, or say helium atoms, at 273 Kelvin and 1 atmosphere. Which of these best shows the speed distribution of argon gas, represented by the dashed line, under the same conditions of temperature and pressure? Okay, so argon would be a more massive gas. So on average, the argon gas should travel slower. It should travel at a lower average speed. So I want something like this first graph, where if I go to the peak, this argon would translate to a lower speed. It's a heavier gas. Helium is at a higher speed. Something like this top graph, where the dashed line would translate into a higher speed. That would be some kind of a particle that's lighter than helium, which, I don't know, maybe like hydrogen gas? I don't know if there's too many other options. This choice, I don't know what this would be. Like here's, I don't know what that is. Maybe like a sample of like, gosh, I don't know, like 2 samples of helium, but 1 sample is a little bit smaller. On average, these guys have the same speed for the dashed line and the solid line. Maybe it's 2 gases that have about the same mass. And again, I would have kind of a similar issue with the last graph, and that the dashed line would represent particles that are heavier, that they're at, or I should say lighter. And the dashed line is at a lower mass because the particles are moving at a higher speed. So in a nutshell, the only point on these graphs that we care about is that peak. And that represents the speed of the majority of the particles. And if I follow it down, I can compare the speed of maybe 2 different particles on 2 different graphs. Here's 2 questions that are very similar. You wouldn't have had both of them, but they're solved the same way. We've got 3 rigid, which means like metal or glass, closed 1-liter containers, each containing a different noble gas at the same temperature. The figure also shows the relative number of particles of each gas in the first 3 containers. So obviously we can't just put like 2 atoms of helium in a container. That's insane. But it's relative, so maybe it's 2 moles of helium. All 3 gases are then combined in a 2-liter container at the same temperature. What is the final pressure in that last container? Okay, so there's different ways of going about this. In a nutshell, I kind of need to know the pressure in each of those 3 1-liter containers. Pressure is dependent on number of particles. As long as the gases are at the same temperature and they're in the same volume container, which the first 3 are, and so it would be relative to the number of particles. So like that first helium container, it's a 1-liter container and it is at 2 atmospheres. And in the first situation on the left-hand side, there's 4 particles. So 4 particles gives me a pressure of 2 atmospheres. Well, then in the middle container, there's half as many particles, so there should be half as much pressure. Okay, so on the left-hand example, if there's 2 moles or 2 atoms of neon, half as many particles, half as much pressure, that should be 1 atmosphere. In the argon container, there would be 12 particles. Okay, well, every 2 particles was 1 atmosphere. So if I've got 12, that should be 6 atmospheres. Okay, so now there's a couple different ways of going about this. We've got the individual pressure from each of the 1 liter containers. Now, if I put all 3 of those gases into just another 1 liter container, then all you would do is add the pressures. That would be Dalton's law of partial pressure that says the sum of the gases would, or the sum of the pressures would give you the total. If I put those 3 gases in a 1 liter container, the pressure would be 9 atmospheres if I didn't change the volume. But I am changing the volume. I'm doubling the volume. So you didn't have to do a calculation. And in fact, this like Boyle's law equation is not in the packet because they just want you to think about it. They want you to kind of think about the relationship between pressure and volume. It's inversely or indirectly proportional. That if I double the volume, the pressure should go down by half. It's double the space for those particles to move and collide. So instead of the total pressure being 9, if I added all of those gases to another 1 liter container, the pressure should be half. It should be 4.5. Now 18 atmospheres might be like if I put all those gases in a half a liter container. Uh-oh. Or now if the volume went down by half, the pressure should double. And it was really similar with the example on the right. Just a little bit different ratio. 6 particles of helium gave you a pressure of 2 atmospheres. So 3 particles of neon would be 1 atmosphere. And then 12 particles of argon would be 4 atmospheres. For a total of 7 atmospheres if I put those 3 gases in a 1 liter container. But if I add them all to a 2 liter container, the pressure would be half. Tricky. But great questions. Understanding the concept of pressure being dependent on number of particles, and then the relationship between pressure and volume. It's like a meaty question, isn't it? Here we had 2 samples of helium in identical containers at the same temperature. Which sample would deviate most from ideal behavior? So ideally, gas particles are not supposed to interact with one another. But if I force them to be close to each other, now those intermolecular forces could become more significant. Now, how do I get gas particles closer to each other? Well, I could put them in a smaller container, which here they're the same container. I could reduce the temperature, so then the particles have less energy and they would contract a little bit. Or add more gas. So here in container 1 or sample 1, when I've got a lot more gas particles, well, if there's just more particles, then of course they're going to be closer to one another. And that would make their intermolecular forces a little bit more significant. Oh, interesting. All right, so I think we'll kind of pause it there. There's the multiple choice. And then I'll bring you the free response.